Good evening, here yet again for another lovely session of CENG 3325 Structural Analysis. So today, or this evening, we're going to continue on with our discussion of the method of virtual work, and we are going to look at virtual work for beams, and I want to work through a few examples of this. So in the previous lecture, lecture 18, we worked through the theory of the method of virtual work, applying it to beams, and now I'd like to apply this in a couple example problems. So let's apply this to a few example problems. So virtual work for beam or for beams examples. I have two examples I want to work through. Both of them will involve statically determinate beams. Now, I did mention previously that the method of virtual work can be used for indeterminate beams, and it can, though that's something we're going to look at later when we get to the force method. There's a method for solving statically indeterminate beams known as the force method, and other structures as well, not just beams. I'm going to save that for a lecture all on its own. So let us consider a beam here. Let's work through, again, I have two examples. One is going to be to solve for the deflection at a single point, and the other is I'm going to work to solve for the deflection at any point along a particular beam. So I do want to show that virtual work can be used for in more of a continuous application rather than just finding it at a single point. So consider a beam here. And I'm going to have a 12 kip point load on the left end of the beam, or towards the left end of the beam here. So a 12 kip point load here, and I'm going to have ends A and end B. End A and end B. And I'm going to give this a relatively simple set of dimensions of 5 feet, 5 feet, and 5 feet. 5 feet, 5 feet, and 5 feet. And we're going to be interested in this point C here. And we're also provided that the moment of inertia of the beam is 120 inches to the fourth power, and that E, our modulus of elasticity, is 29,000 KSI. So another steel beam. So all this is provided, and we want to find the deflection at point C. That's why I've indicated point C here. The deflection at point C. So let's just go through our series of steps that we defined previously in the previous video. If you haven't seen that, you might want to go and pause this and take a look at that previous one. So the first one is going to be just to analyze our real system. Again, just like we did with trusses, this is going to be the system with the real loads applied to it, or the beam with the real loads applied to it. So, and I'm going to do this by a simple bending moment, shear and bending moment diagram. I'll just use the method of inspection for this. So let's draw a free body diagram first. And I'm just going to go ahead and show the reactions on here. This is fairly easy to get. Well, if we have a 12 kip load here, basic equilibrium can show that we'll have an AY here equal to 8 kips, and a BY here equal to, that's going to be 4 kips. So we have a vertical load on the left hand, or vertical reaction on the left hand side equal to 8 kips, and a vertical reaction on the right hand side equal to 4 kips. Then, in turn, I want to get the shear and moment diagram. Now, what I'm really after is the shear and moment function. If I had any more complex loading than this, I'd probably go ahead and just do a integral, but this is simple enough, just a simple point load, that I think I'm just going to go ahead and do the diagrams by inspection and then get the equation from the final moment diagram very easily. So here, our shear diagram. Again, this is going to be our V in kips, our V in kips, and our moment in kip feet. Our moment in kip feet. So we're going to pop on up here at 2.8 initially, and then after 5 feet, I'll go ahead and put the dimensions on here. This is 5 feet and 10 feet. Then we're going to remain constant over to the 12 kip load. We're going to drop down to -4, and then we're going to remain constant all the way to the right-hand side of the beam, where that load on the right-hand side will cause our our shear to jump back up to 0. Then I can get the moment using an area approach. The area, again, this is 5 feet and 10 feet. So the area of this first region here, 5 times 8 is 40. So I know the moment here is going to be positive 40. Positive 40. And then we have an area of negative 40 in this region, so our our moment will decline down to decline down by negative 40 back to 0. So we'll have positive moment throughout, positive bending throughout. And for a simply supported beam, that's exactly what we would expect, unless we had something with, say, a negative load or something. So we have that, and I can very easily then get my real loading, or my real moment, I should say, my real m of x. M of x, remember from the previous video, m of x is the moment in the beam, the moment function that results from the real loading. And this is then going to be equal to 8x. We can find that just these again. This is just mx plus y equals mx plus b type equations. If I know that we're at 0, 0 here, and that would be 5, 40, and 15, 0. I can find that the moment function is 8x when x is in the first region, between 0 feet and 5 feet, and then it will be negative 4x plus 60. Negative 4x plus 60 when x is between 5 feet and 15 feet. So this is our m of x here, our m of x function, at least for our initial case. We will later resolve this though. So the next thing I want to do is analyze the virtual system. Again, I have my m of x. This is the moment, the interior bending moment in the beam as a result of the real loadings. Second, I'm going to analyze the virtual system. And I'm going to try to get my mv of x, m sub v. So let's analyze the virtual system. And let's consider our beam first, or let's draw this out as a free body diagram. So let's see here. I'm going to have a 1 kip load. I have my units in kips, so I'm going to apply, my unit load is going to be 1 kip. Then if I have my dimensions of 10 feet and 5 feet, again by simple statics you can find that the reactions on the left hand side will be 1/3 kip, 1/3 kip, and 2/3 kip on the right hand side. So we have 333-ish pounds on the left hand side and 666-ish pounds on the right hand side, and 10 and 5 feet. Next I want to get the shear diagram. So let's go ahead and get the shear diagram. And I'll go ahead and draw a beam space for I'll go ahead and draw the beam for the moment diagram as well. So here, V again in kips, and M in kip feet, and M in kip feet. So initially we're going to have, and again I'm just going to do these via inspection. And I have, so where our transition region is going to be there, our discontinuity is there. And so we're going to jump on up to 1/3 from the initial load. Then we're going to be constant all the way to our point load, at which point we'll drop down by 1 kip and be down at negative 2/3. Then we'll remain constant at negative 2/3 all the way to the right hand side of the beam, where we'll jump back up to 0. 2/3 kips. And actually I think I'm going to write this a little bit lower so I have some room. And in kip feet. So our loading then, we have our loading and we have our shear, and now let's again use the area method to find our moment function, or to find our moment. The area of this, the height is 1/3, the width is 10, so we're going to be up to 3.333, or 10 over 3. So 10 over 3. Again, we're starting at 0 on the moment because this is a pin support. The area of this is positive 10 over 3, so we're going to increase from 0 by 10 over 3, ending up right at 10/3. And of course, if this is going to be a linear function, because the integral of a constant value function is a linear function, then the area of this is 5 times negative 2/3. Probably should put a negative there. And that's going to drop us down to negative 2/3. And again, we'll have positive bending moment throughout, even with the virtual system. So no great surprise there. And if you do a ordered pair analysis, or just not an ordered pair analysis, that sounds way more complex than it needs to be. That's just finding the functions via ordered pairs using y equals mx plus b, literally algebra 1 here. So mv as a function of x, I'm going to have two regions. I'm going to have the region between 0 and 10 feet and the region between 10 feet and 15 feet. And so mv as a function of x is going to be 1/3 x when x is in the first 10 feet, so between 0 feet and 10 feet, and then negative 2/3 x plus 10 when x is between 10 feet and 15 feet. When x is between 10 feet and 16 feet. So we now have our function for our virtual loading and the function for our real loading. And the next step is going to be to resolve any zone disputes, or zoning disputes. That sounds a wonderful term for this. Or more importantly, resolve any differences in our zones. So you notice here, on the virtual loading, we have one zone from 0 to 10 and one from 10 to 15. Here we have one zone from 0 to 5 and the other from 5 to 15. So what I really need to do is I need to break these into 3 zones rather than 2. So let's go ahead and do that, and really that's not too difficult. It's just repeating things essentially. So 3, resolve the zones, resolve into the final zones of integration, or just resolve zones of integration. So if I do that, I'm gonna need to break apart on my on the real loading, or the moment from the real loading. I'm going to need to break up the second zone. The second zone on the real loading currently has one zone between 5 and 15. I'm going to break that into 2 identical zones, or 2 zones of identical equations or expressions. So 8x will still exist from or be indicated from 0 to 5 feet. But then I'm going to split up this negative 4x plus 60 between x equals 5 and x equals 10. So between 5 and 10 feet, and then an identical one in the last 5 feet of the beam. 10 feet is less than x is less than 15 feet. Then mv as a function of x, the virtual loading, or I keep saying virtual loading, I mean the moment from the virtual loading. Here it's the first zone that I'm going to have to break into. Originally I had one zone from 0 to 10 and another zone from 10 to 15, and I'm going to have to break that first 10-foot zone up into 2 5-foot zones. So I'm going to have one zone of integration of 1/3 x from 0 to 5, another zone with the same value from 5 to 10, and the final zone that is distinct, 2/3 x plus 10, between 10 and 15 feet. And now we finally have our complete and compatible expressions for both the real and the virtual moment. So the next step is going to be to apply our actual equations of virtual work. And this will really be our final step. So for apply the virtual work equation, apply the virtual work equation. Now, I recall, as we discussed previously, that the equation for beams is going to be 1 times delta is equal to the integral from 0 to L of mv times v divided by EI. And to make things simpler for now, I'm going to go ahead and pull out that EI. Oh, of course, our dx, can't forget that. I'm going to go ahead and pull out the EI because those are just constants. They're not going to affect anything. They don't vary as a function of x. So I'm just going to go ahead and pull them out. MVM dx. MVM dx. And then I'm going to put in my, my terms from earlier. I'm going to substitute in expressions for MV and M. And I am going to need to break this into 3 separate integrals. So I'm going to give myself plenty of space here to write, and write kind of small. 1 times delta, again, delta is the final thing that we're looking for, will be equal to 1 over EI times the term, well, 1 integral from 0 to 5, and that's going to be 8x times 1/3 x dx. Again, I'm just matching the individual M1, M2, M1, MV1, M2, M1, MV1, M2, MV2, all of those things. Plus the integral from 5 to 10, that's going to be negative 4x plus 60 times 1/3 x dx. Plus the integral from 10 to 15 of, that's going to be negative 4x plus 60, and then negative 2/3 x plus 10 dx. And you can go ahead and solve these in whichever method that you please. And if I go ahead and collapse those down, if I solve for those definite integrals, I will get, for the first one, it comes to 111.1 repeating, essentially. I'll go ahead and do that. Plus 361.111 plus 111.111 again. And I would like to list the units on this. So moment fundamentally has units of kip feet. So I know this term must have units of kip feet. I didn't carry my units all the way through, but I do know that this should have had units of kip feet, and this should also have units of kip feet. And if we integrate, so that would give kips per kip squared per foot, or kip squared foot squared, just from this. And then when we integrate across x, we're going to get one more foot, one more unit of foot. So we're going to have units of kip squared foot to the 3rd power. And the reason I'm doing this is because we're going to need to pay very close attention to our units in these things. And so here, then we're left with 1 times delta is equal to 1 over EI times, if we combine all these together, 583.333 kip squared foot to the 3rd. Kip squared foot to the 3rd. Now, I need to take into account my E and my I. I need to convert those to compatible units. So the real problem is my length unit. I have feet here. And the problem is my E is going to be in kips per square inch. This is 29,000 KSI, or kips per square inch. So I need to convert from kips per square inch, but to KSF, kips per square foot. So I'm going to multiply the conversion factor by the conversion factor, 12 inches per foot, quantity squared. And this then comes to 4.176 times 10 to the 6 kips per foot squared. Kips per foot squared. Then I is going to be 120 inches to the 4th power. That was what was provided. Then I'm going to multiply by 1 foot. I need to convert this to from inches to the 4th power to feet to the 4th power. 1 foot over 12 inches, so we're going to get a rather small number, to the 4th power. And we are then going to get 0.005787 feet to the 4th power. Feet to the 4th power. And then I can just put all this into the formula. I think I might do this on the next slide to give myself a little more room. I'm going to now do a final workup here, including units. So my 1 is actually 1 kip. I just want to show that the units really do work out on this. Times delta is equal to 1 over EI, which is 4.176 times 10 to the 6 times 10 to the 6 kip per foot squared times, that's going to be here, 0.005787 feet to the 4th power. Feet to the 4th power. That's our moment of inertia I. And then times the combined term that we had previously, or we found previously, of 583.333 kip squared foot to the 3rd. Kip squared foot to the 3rd. So now I'm going to start canceling out some units. First of all, I'm going to cancel out this foot squared, and this 4th is going to become a square. So if I take 583.333 and divide by 4.176 times 10 to the 6th and this, I will get a unit, or a number, that is 0.0241. And I do want to work through the units. Initially I had kip squared foot to the 3rd. I would have that in the numerator. And then kip foot squared. Kip foot squared, and I have 1 kip times delta. And so the foot squared goes away, and this becomes just a foot. That kip goes away, and that just becomes a kip. And so I'm left with 1 kip times delta equals 0.0241 kip times feet. And the kip cancels out, and I then find that delta is equal to 0.0241 feet. And I can go ahead and convert that to inches if I want, and find that the final deflection at point C is going to be 0.290 inches. The final deflection is 0.290 inches. So, working through this, we can see our general method. First, we set up our real system with the real loads, find the reactions, find the moments, and not just the moments, but the moment functions. Second, I go and apply a unit load at the point of interest. Here I wanted to find a deflection at point C, so I went and applied a 1 kip or a unit load at point C, and then I went through your standard static analysis and found the moment functions for the virtual load, so that's the MV, my virtual moment. Next, I resolved the zones of integration. I saw that the boundaries didn't overlap just right, so, and pretty much the only case where things will overlap just right is if the point that you're interested in is one of the ones that has a discontinuity in it. For example, if I had put my if I was finding the moment at this point here where the 12 kip load is applied, then my zones would line up automatically and I wouldn't have to do step 3. But in most cases, you probably will. And then finally, 4, we apply our virtual work equation, adding up the integrals as needed, 1 integral for each of our zones of analysis. We work all the way through and do take great care to make sure units are correct. So I'm just going to go ahead and put an extra note on here, and great big, let's go ahead and do orange. Again, note, watch your units. You simply must watch your units. If there's one thing that's going to screw you up, it's going to be your units. So make sure you're using compatible units. If you can do this 2 ways. One, you can just use inches for your length and keep everything in inches and KSI and inches to the 4th power. Or 2, like I did in this problem, you can leave your length in feet if you like, and then convert your moment of inertia into feet to the 4th power and your modulus of elasticity into kips per square foot. And of course, if you were doing this in metric, you would have to use similar conversions to make sure everything was compatible. But at least with metric, you have an easy way of doing this if you want. You can just use base units for everything. If I was doing this in metric, I'd probably just do everything in meters. So convert all stresses, or convert your I would convert your moment of inertia to meters to the 4th power, just have it like that. or I would convert my my modulus elasticity, just convert that to, instead of using gigapascals or megapascals, just use pascals. It'll be a quite large number, but it'll avoid having any troubles with units. All right, and that is the first example. All right, let's go ahead and work through a second example here. So example 2. So for this, I want to do something a little bit different, and that is to find the deflection in a beam with a, with a deflection in a beam, not at a single point, but at any point along the length of the beam. So I'm going to try to do that using the method of virtual work. So let's consider that here. And this is going to be given. I'm going to have a cantilevered beam for this one, and there's going to be a 5 kip load at the end of it. We'll have a 5 kip load at the end of the beam, and this thing will be 16 feet long, which, to avoid the problems with units, I'm just going to right off the bat convert this to inches. So this is 16 feet. And this is also equal to 192 inches. So I'm just going to go ahead and do all the math in inches. So my moment will be in kip inches instead of in kip feet. And also we're told that the beam is also made of steel, just like the previous one. I kind of like steel beams. 29,000 KSI. And also the moment of inertia I is equal to 220 inches to the 4th power. 220 inches to the 4th power. And I wish to find the deflection at any point along the beam. Along the beam. So rather than simply at one single point, like we've done in the previous examples, I want to find the deflection at each and every point along the beam. So in other words, I'm going to be solving this for a general case. So step 1 is going to be to analyze the real system. No change there. Step 1, let's analyze the real system. So this is going to be just the same as previously. And I'm going to go ahead and create a free body diagram of our beam, and then find our shear and bending moment diagrams. And this is going to be very simple for this beam. We will have a 5 kip load on the end here. We'll have our 5 kip load at the right-hand side of the beam. And then we'll have a 5 kip vertical reaction at the fixed support. Then we'll have a moment, because this is 192 inches, again, 5 kips here. And then if you take the moment of that, multiply 192 by 5, you will find there is a moment, a counterclockwise moment, of 960 kip inches at the left-hand side of the beam. Next, I want to find the shear diagram. And this is going to be fairly simple. So this is, again, the free body diagram, and then the shear in kips. And let's go ahead and find this. So I'm going to have, we're going to start up at 0, that we're going to pop immediately up to 5, and then there are no other transverse loads across the length of the beam, and so we're going to end up with a constant shear all the way across until the load on the right hand side causes us to drop back down to 0. So 5 kips here. And then for moment, it's just going to be a triangular moment. So our moment here, we have M in kip inches here rather than kip feet. And we're gonna start down at negative 160, and we're going to just increase linearly back up to 0. And again, it will be negative because even though we have a positive reaction applied to the left-hand side of the beam, the internal bending moment will be opposite of that, and that will be negative. So we'll start at negative 960, and then we'll linearly increase to 0. So negative 960 here. And so then we can immediately get our m as a function of x. M as a function of x is going to be equal to negative 960. And if you do just an mx plus b, find the slope of this, you'll find this is plus 5x. It has a slope of positive 5. Again, this is just literally algebra 1. You have one ordered pair at 0, negative 960, and another at 192, 0. And if you do that, you run through the math, you'll find that you get an equation of m as a function of x equals negative 960 plus 5x. But this, again, is not in kip feet, but in kip inches. I'm approaching this problem doing everything in kip inches, or everything in inches, rather than in feet. So that way I'll be able to avoid the unit conversions later. So step 2, I want to analyze my virtual system. Now this one is going to be a little bit different than the previous one, because we're doing this as a general case for the load at, not at one particular location, but for the load at any, I don't want the deflection at just one location. I want an equation that will give me the deflection at any position. So 2, let us analyze the virtual system. Let's analyze the virtual system. So the big idea here is that I'm going to place a virtual unit load, just like we had before, but not at any particular location. A distance that I'm going to call A, just an arbitrary distance A, from the left-hand side. Now, I want to make sure to do this as A. Well, actually, let me draw it out first, and I'll comment on why it would be good to do this as A versus X. So let's draw a free body diagram first. And the only load on this beam is going to be a 1 kip load at a distance A from the left-hand side. So 1 kip and a distance of A. And then in the, in our reactions at our fixed support, we're going to have a shear, or an AY, if you want to call it that, of 1 kip, and then a moment. Our reaction moment is going to be 1 times A, or simply A. So we have a reaction moment of basically A kip inches. Now, why didn't I use X here? That is tempting to use X, but the problem with that is I am going to already have to integrate as a function of X. I'm going to have to integrate our moment functions down the line with an X dx. And so that integration, we're really trying to integrate the moment, not the actual A. A is a constant. Regardless of where you analyze your dx, the distance of this unit load is not changing. It's still just at position A. So we're not trying to figure out what would happen to the beam as we move the deflection all the way down the beam. I just want to include this as a constant, so I don't want to have that baked into my my x dx equation. So it is imperative that we use this as a constant A, and that's not going to be integrated. We're going to still integrate as a dx, so things aren't going to be too complicated. Then let's go ahead and get the shear diagram. So V and kips, and our shear diagram. On the left hand side, we're going to jump up to 1 kip, then we're going to remain constant all the way over to our unit load, wherever that happens to be. Then we're going to drop down 1 kip and end up at 0. And this is going to have, let me go ahead and mark this as 1 kip, 1 kip, and this is going to have a width of A. Again, we don't know the exact width of that. It'll just depend on where we're trying to find the deflection at any given time. Then let me find the moment. And of course, this is a cantilevered beam. So beyond the location of our furthest most load, we have no more moment and no more shear. So because this load is not at the end of the beam, we will actually only have moment and shear over this first region of the curve, or of the diagram. And then for reaction, or sorry, for our moment here, M in kip inches our moment here, well, first of all, we're going to drop down to negative a. We're going to drop down to negative a, again, because we have a counterclockwise moment of a applied at the left end as a reaction, but the internal moment is going to be negative a there. And then the area of this is 1 times a, or simply a, and it will linearly increase up to a here. And so let's just go ahead and run through getting the moment function. Well, if I want to get the slope of this, I know that mv as a function of x is going to be mx plus b, and I have 2 points of interest here. I have 0, negative a, and I have a, 0. So I have 0, negative a, and a, 0. This is, again, length a, or width a. And so my slope is just going to be 0 minus negative a, or plus a, divided by a minus 0. And so we actually find that our curve here is going to have a slope of exactly 1, which, since it's going from negative a to a, shouldn't surprise anyone. And of course, our intercept of y equals mx plus b is going to simply be negative a. So we have a very interesting moment expression here, and that's going to be that mv, well, it's still going to be a piecewise function here. See, we're only going to we have one region from 0 to a, but then beyond that, the moment's going to be 0. So our virtual moment function will be x minus a, because we have a slope of 1. When you put that with x, or put that as m, we'll just get x. So we'll have a moment of x minus a when x is between 0 and a. And we'll have a virtual moment of just 0 when x is between 0 and, between a and the beam length of 16, or I should probably say 192 inches. 192 inches. So the third step is going to be, as before, to resolve the zones of integration. So no real difference here, except we're just doing this in more general terms for our virtual moment. So resolve boundary conditions. I could call this many things. I could call it resolving the boundary conditions. I could call it resolving zones of integration, whatever you want to call it. But let's resolve them. And looking back, our real moment only had one zone. There were no discontinuities between the left hand and right hand side. But because my virtual moment does have 2 zones, I cannot talk right now. I'm going to have to go ahead and break the real moment into its 2 independent but identical zones. So m as a function of x is going to be negative 960 plus 5x in both regions, negative 960 plus 5x, 5x and 5x, and this will be when x is between 0 and a, and this will be when x is between a and 192 feet, or 192 inches, I should say. 192 inches and 0 inches. And then our virtual moment will be the same one we had before. We don't need to adjust this at all, but I'll just go ahead and write it for the sake of completion. So it will be x minus a, again, when x is between 0 and a. And it will be 0 when x is between a and 192 inches. Between a and 192 inches. Then step 4, I'm going to apply the principle of virtual work, or the equation that we have for virtual work. And so we recall that our equation is 1 kip times delta, and I'm just going to go ahead and call this delta A, the deflection at location A, is equal to 1 over EI times the integral from 0 to L of mv dx. And I'm gonna give myself plenty of room. So I will have 1 kip times delta A is equal to 1 over EI. Again, I'm going to break this into 2 added together integrals, but pulling out the EI as a factored constant. 1, the integral from 0 to A of negative 960 plus 5x times x minus a dx. and another integral, the integral from a to 16 of negative 960 plus 5x times the virtual moment of 0 dx. And look what happens. Interestingly enough, because our virtual moment in the second region is 0, this entire integral drops away. That makes our job a lot easier. That entire integral drops away. And so, and this one kip, we'll just say that disappears as well. I'm not carrying my units all the way through on this one, but I by avoiding using by using compatible units at the start, I don't have to be so careful about tracing my units all the way through. So I'm left with 1 over EI, 1 over EI times the integral from 0 to a of negative 960 plus 5x times x minus a dx. And this is also equal to, let's see, 1 over 29,000 times the moment of inertia of 220, and this is KSI, times the moment of inertia of 220 inches to the 4th power. 220 inches to the 4th power, times the integral we had before, the integral from 0 to a of negative 960 plus 5x times x minus a dx, times x minus a dx. And multiplying all this out, I will get 1.567 times 10 to the negative 7. And this integral, if you work this out, carrying a through, we'll get a final integral of 480 squared, or 480a squared, I should say, minus 0.8338 to the 3rd power. A to the 3rd power. And therefore, delta A, combining this together, we'll find that delta A is equal to 0.000075 a squared minus 1.306 times 10 to the negative 7 a to the 3rd power. Or if I wanted to express this as a deflection as a function of x, here if I wanted to, I could go and bring back x because I'm done integrating across x, so I could just convert x to a if I wished. And this would be, let's see, that would be then 0.00, or let's just call that 7.5 times 10 to the negative 5th a squared. I guess I don't need my brackets anymore here. 7.5 times 10 to the negative 5th a squared minus 1.306 times 10 to the negative 7 a to the 3rd. And I could report this as our final complete deflection equation. Oh, I probably should write that as x if I'm going to put it as in terms of x. So my final deflection is 7.5 as a function of x again, is 7.5 times 10 to the negative 5th x squared minus 1.306 times 10 to the negative 7, or e to the negative 7 if you prefer. And I can box that. And if I wanted to know the deflection at a particular point, as an example, if I go and find the deflection at the end of the beam, which is at x equals 192 inches, I will find this is at a reasonable value of 1.849 inches. The final deflection at the end of the beam is 1.849 inches. That wasn't asked for, but it is good to illustrate how this would work. Actually, I think I will do one final problem here. I know I said that I was going to do 2 problems, but another one has occurred to me, and I think I'll try working through this one. So this is kind of a oddball problem, but I think I might try working through a beam using the method of virtual work and use it on a particular type of beam, a tapered beam. So let's do a virtual work for tapered beams. And this is just to show really the flexibility of the virtual work method. So let's consider a problem with a tapered beam. Now, if you're not familiar with the terminology, a tapered beam, of course, is one where the cross-section is not constant. So given this, let us say we are given the following. I'm going to have a fairly simple loading, a simply supported beam, And let's say there is an 18 point load in the middle. And this has dimensions of 6 feet and 12 feet. And I'm going to go ahead and do this one all in inches like I did the second problem. So 6 feet, and that's going to be equal to 72 inches. And 12 feet, and this will be equal to 144 inches. Equal to 144 inches, and we have an 18 kip point load here. And I wish to find, let's find the deflection at point C. And point C, for simplicity, I'm going to have it right where the point load is applied. So we won't need to worry about any kind of overlapping boundary zones this time. Find the deflection at point C. And also we're told that this is a different modulus of elasticity than the ones we saw previously. This one's actually going to be made of concrete with a modulus of elasticity of not 29,000 KSI, but 3,300 KSI. 3,300 KSI gives per square inch. Okay, but the final really interesting thing about this is that the cross section is not constant. So I'm going to give us a beam that has a non-constant cross section. So let's say we have a beam, and we are told the following: the cross section at A. We're given two cross sections and told they linearly vary between them. So at A, we have a cross section like this. Oh, I would like to get a nice rectangular cross section. Rectangular-ish. It's 6 inches wide and 12 inches high. So it's a concrete beam, 6 inches wide and 12 inches high. And for whatever reason, this beam is then constructed at B, and this is A, and this is B, and I probably should use capitals. I usually use the capitals for my points. A and B. At B, it has a cross section that's reduced to a square. 6 inches and 6 inches here. And this is concrete, so I'll put lots of dots there to show it's concrete. If you want to know more about concrete design, feel free to take a look at our videos on reinforced concrete and steel design. CENG 4412. There's a playlist on my channel for that. Anyway, let's consider the cross section. So what's going to happen here is that the depth linearly decreases. So the width is going to stay the same, but for whatever reason, the depth starts out at 12 inches on the left side here, and it linearly decreases to 6 inches on the right side here. Now, I don't know why you would do this for a simply supported beam. That's a bit unusual for a simply supported beam. Maybe you have something where there's way more load over here, but even then you'd have problems with shear. And anyway, this is just an example problem. Where you tend to see more tapered beams are things like, I tend to see them in like light metal buildings, manufactured metal buildings, that sort of thing. But then you tend to have more of a taper, almost like a double taper, where there's maybe a thicker cross section here, and then both taper toward the middle. But I want to keep things relatively simple. This is going to be complex enough as is, so I thought we would just have a relatively simple taper where it was just linearly decreasing. So we're going to need to work with this, and let's just start at it. So solution. Now, the first thing we're going to need to realize is that we are not going to be able to use the exact same method we did previously. Making the moment of inertia non-constant throws all of this for a loop. See, if we remember our previous formula, it was 1 times delta is equal to the integral from 0 to L of mv m over ei. But in our previous examples, dx of course, in our previous examples, we had taken out the 1 over ei because those were constants across the beam length, across our integration, and we could just do mv times m dx. We cannot do this here because our moment of inertia now actually is also changing with x. So we're going to have to do some really interesting math to make all this work. So the first thing we need is the moment of inertia as a function of x. Need moment of inertia as a function of x. I as a function of x. Now, the first thing to do will be to get the beam height as a function of x, and then once you have that, we can very easily calculate the moment of inertia. So, the height of the beam as a function of x, let's see, let's just say this is mx plus b for now. It is going to be linear, and the m is going to be 6 minus 12, just calculating this, over 216 minus 0. Where that comes from, again, that's just the slope. I know on the right end of the beam, it has a depth of 6 inches at an x-coordinate of 216. On the left end of the beam, I know it has a height of 8 inches, and that's at x-coordinate equals 0, so we get a slope of negative 1 over 36. And just looking at this, we know that b, because the beam height starts out at 12, our b here for the y equals mx plus b is going to be 12 inches. We have an initial y-intercept of 12 inches. So therefore, h as a function of x is going to be simply negative 1 over 36 x plus negative 136x plus 12. And that's all fine, but the real problem is that moment of inertia is not going to be linear. So our height may be linear, but our moment of inertia is not just proportional to height. If you remember back to your mechanics of materials, I remember that the moment of inertia for a rectangular cross-section is equal to 1/12 bh cubed. The moment of inertia for a rectangular cross-section is 1/12 bh cubed. And so our h here, though, is a function of x, so we're going to have to substitute this into our I expression. And so that will be 1/12. Now, thankfully, the b isn't changing as well, otherwise this would be even more complex. And this would then be 6 inches. And then negative 1 over 36 plus 12, and all of this taken to the third power. And if you then combine this, multiply this, and expand this, you will get a value of, let's see, the exact form of this is going to be negative x to the third. Now you could do this as decimal if you want, but I just decided to give you this in exact form. Okay, here it is. It's a beast. Negative x to the third divided by 93,312 plus x squared divided by 72 minus 6x plus 864. Isn't that lovely? And so this is the moment of inertia as a function of x, and this is in inches to the fourth power. So this is built to have inches, your x inputted as inches, and the final output will be inches to the fourth. And if we double check this, if we put in 0, we'll get a moment of inertia of 864, and if we put in x equals 216, we'll get the appropriate moment of inertia on the right-hand side of the beam as well. So this is the only really complex thing. Everything else will proceed relatively smoothly. So again, our first thing was to get our moment of inertia as a function of x. 2, I want to work with the real system. And working with the real and virtual system are going to be no different than what we worked with previously. So real system now. Not a Y, it looks like a T. So let's get the real system. And first I'm going to get a free body diagram. We'll get a free body diagram. And then let's just say then a V in kips, and a moment in kip inches. In kip inches. And I'll go ahead and do these in red. So our free body diagram, it's very easy to find the reactions. The left-hand side reaction will be 12 kips. We'll have our 18 kip load at 6 feet from the left, or 72 inches. We do need to make sure to do all of this in inches. Again, to maintain unit cohesion, or unit cohesiveness, compatibility of units, probably a better way of saying that. Unit cohesion, that sounds something like in the army or something. That's not quite right here. So anyway, let's say we have a distance of 72 inches here, and a distance of 144 inches here. Again, these are just the distances from previously, but in inches. So the shear then, we're going to initially pop up to 12. Then we're going to remain constant all the way across to negative 8, all the way across to 18. We're going to drop down at 18 to negative 6, and we're going to remain constant all the way to the right-hand side, where we'll bump up again to 6. And the dimensions here will be 72 inches and 144 inches. Then the moment, again, the area of this 12 times 72, you'll get an area of 864, or 864 kip inches. So we'll have a peak value of 864 kip inches, and you'll also find that negative 6 times 144 is also negative 864, or is negative 864, and so that will linearly decrease to this. And so we have a linear but positive moment throughout, which is typical for our deflection curves, or for our unit well, I guess this is not a unit, sorry, we're not in the virtual system yet. But again, we just have a single point load in the middle, so nothing really new there. And if you get the moment functions, again, just via y equals mx plus b, or whatever your preferred method might be, you can get that the moment as a function of x for the real system is 12x when x is between 0 and 72 inches, and negative 6x plus 1296 when x is between 72 inches is less than x is less than 216 inches. Is less than 216 inches. So again, 216 inches is the total length of the beam, and these functions can be obtained simply by using y equals mx plus b and known ordered pairs. Our ordered pairs are 0, 0, 2, 16, 0, and that would be 72, 864. Then, the third step, I suppose, is going to be to look at the virtual system. And this is very similar to what we've done before. So I'm going to breeze through this one a little bit. We have our virtual system with a 1 kip load here, the 1 kip unit load, 72 inches from the left-hand side, and 144 inches here, with our 2/3 kip on the left and a 1/3 kip on the right. And so that's our free body diagram. And then we have a shear V in kips. And we'll initially jump up to 2/3. We'll remain constant over to the 1, where we'll drop down to negative 1/3. And we'll remain constant over to the end, where we'll jump up again. Then our moment, again based on a simple area approach, moment in kip inches. Initially this will jump up to, let's see here, that should be, I should have my dimensions of 72 inches and 144 inches here. Our area, if you multiply 2/3 by 72, you'll have 48, so we'll be up here at 48, and then we'll increase linearly to it and then decrease linearly from it. So 48, extra big point there, and then linearly decline down. So we have that, and if you go and get the functions for this, you will find that the virtual moment as a function of x is equal to 4x when x is between 0 and 72 inches, and 72 inches, and it will also be equal to negative 1/3 x plus 72 when x is between 72, let me put that on the other side, maybe something like this, 72 inches is less than x, which is less than 216 inches. Now our normal step at this point is to resolve the boundaries, but in this case we don't have any real boundaries to resolve. We do have boundaries in our zones of integration, but I decided to make, but again when setting out this problem, I decided to make things a little bit simpler because we are dealing with the complex moment of inertia situation. So I decided to ask us to find the deflection at C, which is the exact location where the point load is applied. So our by lieu of this, our zones of integration between the virtual and the real load automatically overlap. But I'll go ahead and rewrite them here, just for clarity. Actually, that's step 4 again. Resolve boundaries. And m as a function of x is here and here, and then mv as a function of x is here. Jumped ahead there. So m as a function of x is 12x when x is between 0 and 72 inches, and negative 6x plus 1296 when x is between 72 inches and 216 inches. And then in the virtual moment side, it will be equal to 4x when x is between 0 and 72. And it will be negative 1/3 x plus 72 when x is between 72 and 216. Again, all of this is using kips and inches, and that way I don't have to worry too much about unit conversion. So if you just right off the bat use a consistent unit system, you'll never have to do unit conversion, and you don't necessarily have to carry your units all the way through, which does make this keeping track of this a lot easier. So finally, step 5, I am going to apply the virtual work equation, and maybe I'll do that on the next slide actually. Step 5, apply the virtual work equation, and this is where things get fun. So apply the virtual work equation for certain definitions of fun. So 1 times delta is going to be equal to the integral again from 0 to L of mv m over ei. And again, the crucial difference between this problem and the previous ones is that I is not constant. So we're going to have the integral from 0 to 72 of 12x times 4x in the first region. And our modulus elasticity is going to be 3300 ksi, not 33,000, 3300 ksi. And then we'll have, of course, have our dx. And now I get to shoehorn in that entire long equation. Negative x to the third divided by 93,312. What a lovely equation this is. Plus x squared divided by 72 minus 6x plus 864. Plus the integral then from 72 to 216. Times negative 6x plus 12, oh, that is not a very good 6, negative 6x plus 1296 times negative 1/3 x plus 72 dx divided by our modulus elasticity of 3300 ksi and times our ridiculous moment of inertia equation of negative x to the third over 93,312 plus x squared over 72 minus 6x and plus 864. Now, doing these integrals, well, these would be tricky to say the least. I would not want to try to do one of these integrals by hand. I am not going to do one of these integrals by hand. This is the kind of integral that's best solved via numeric analysis. So, especially because we're not looking for a definite integral, an indefinite integral. We're looking for a simple definite integral. And so this is something that I would just throw into either a calculator that can do integrals like an 89 or 92, or you could use a software package like Maple, MATLAB, whatever it might be. This is one that you could use Wolfram Alpha. I imagine it can probably handle this without much difficulty. It can do some pretty crazy stuff. So yes, this is not one that I would want to tackle by hand, although I suppose you could if you were really determined. But anyway, it's late enough as is. I do not feel like doing that beast of an integral this late at night. So I'm going to go and just give you the final results of what I got when I ran this through a numerical program, or aka my TIA9. And I got a delta equal to 3.15 inches plus 1.743 inches. So this whole, especially when we divide by the one kip, this would be left with kip inches basically. Actually, let me just go ahead and show that for consistency. I had my one kip basically here, and this would effectively have come to kip inches, and this would have effectively have come to kip inches. Kip inches here. And adding those together, we would get 4.89 kip inches, and then 1 kip times delta. That would cancel out, and the kips would cancel out, and we would get a delta equal to 4.89 kips. Or sorry, 4.89 inches. And that would be the final desired value. And this isn't necessarily the maximum deflection. This is just the deflection at our point of our load application. And that could be the point of maximum deflection, but there's no reason it has to be. So as you can see, this is actually quite a large deflection. So I'm not sure why you would, again, this would be a very odd way to set up a beam and support a beam this way, and that's probably why we would end up with such silly deflections. So you'd end up with a much reduced deflection if you used a continuous 6-inch by 12-inch beam, and I don't want to think of what it would take to actually fabricate a tapered concrete beam like that, but it would not be fun. I don't want to do that, so let's not worry about such things. But there are cases where, as structural engineers, you may need to calculate the deflection or the behavior of a tapered beam. And so for this particular problem, the deflection ended up being quite large. For a beam of that span, that would probably not be a satisfactory or allowable deflection, so you'd have to go back and redesign the beam. For example, the easiest way to redesign it would be, oh, let's just get rid of the stupid taper. But anyway, that'll do it for now. So I hope you all enjoyed this. I know this was a bit of a surprise third problem. Hope you all liked this. If you have any questions, feel free to contact me. Those in my class this semester. Thank you for sticking with me through this. Thank you all for watching. I hope you all enjoyed this. I'll see you all again later. And as always, thank you.